Hello everyone. In this video we'll be discussing sets, or otherwise known as set theory. So there's actually quite a lot to discuss in this video. We'll be taking a look at what a definition of a set is here, and then some properties, different definitions of things involving sets, and maybe even some operators. Maybe actually operators we'll discuss in the next section more than anything, but we will take a look at some properties of sets for sure. So I say here a set is just a list of things in the set which are known as elements. So here, for example, the set 1, 2, 3, and so on, these are the elements of that set, the things that are contained in that set. So everything separated by the comma is an element of the set. Okay. Now, for this one in particular, this is kind of, I don't know, it's a little bit of a weird thing for me, because for me, this set is known as the set of natural numbers. Natural numbers. The reason why I think that's weird is because the book we're using for this course doesn't define natural numbers to be this. It defines 0 to be a natural number. For me, 0 is what is called a whole number, not a natural number. But because the book defines that, then I guess we'll be using that for this class. But I will probably have to emphasize that every now and then just so we understand what our definition of natural number is. Either 0 is included or it's not. And it's a big debate, honestly. If you were to look it up, you'll see that some people believe that 0 is not a natural number. Some people do believe 0 is a natural number. I would like to say, this, or we could say it's this with or without 0, and it just kind of depends. Maybe what I think is actually a way better kind of in between is that the set of natural numbers is the set of positive integers starting with 1, and including 0 is labeled as n0. So I actually think we'll adopt this notation for the class. Even though the book says this is just n without the 0, I think this is, a better kind of in between, just to kind of avoid that confusion and that controversy. Okay, moving on. Capital A is a set of A, B, and C. And the United States is a set of, the U.S. states, so the states of the United States, what I meant to say here, is a set of all of these 50 states, so Arizona, California, Colorado, and so on. Okay, and now I go on to say that this symbol here, it looks like a little E. Let me kind of blow that up so we can see how it looks. Looks like a C with this line through it. It looks kind of like an E. This means element of. So X, E, S, this is really known as epsilon. So X epsilon S means X is an element of S. Okay? So for example, Nevada is an element of the US states. D is not an element of the set ABC because D is not contained in there. So notice this is not an element of. Not an element. I'll use ELT for element of. So slash through it negates that kind of. And then this last one I wanted to kind of show before we get into the next screen, this precise interpretation of set by what is called set builder notation. So first we have what our elements are, and then conditions on our elements. So this is the set of all numbers x. This colon means such that. Sometimes a bar is used instead. I actually like using the bar. The book we're using uses colon, but bar or colon, they mean the same thing. So x such that x is in between 0 and 5, but could be 5. So this is the set of all numbers in between 0 and 5, with a possibility of being equal to 5, but not to 0. So 5 is definitely an element of that set. And by the way, if you recall from algebra, interval notation, this is just the interval 0 to 5. Bracket on 5 because we're including 5 here. Now, technically, when you don't say anything on x, we just kind of assume x is any number you can possibly think of. So I'll probably actually say that x is a real number. So just like n is a set of all natural numbers, whether you choose to or not include 0, doesn't matter. R is a set of all real numbers, which is any number you can think of that lives on the real number line. We'll discuss this in more special sets in the next video, or in the next board right now, amongst a few other ideas. So let's see that right now. Right, so here I have a lot of different symbols to discuss, but I don't really have too much space for any examples of them. Maybe I'll do an example on the next screen, perhaps. But I think what I want to do right now is maybe kind of give an explanation of what these are and maybe talk a little bit about an example as we go along, possibly. So here we have some special sets. There's empty set, universal set, natural numbers, integers, rational numbers, real numbers. These two we kind of mentioned last board. And then the power set of a set A. So empty set is the set that contains nothing. So you can think of this as, I didn't mean to put a 0 here, by the way. You can think of this as a set that has no element. So the set, that's actually a good example because the set that contains 0 is not an empty set. It has one element. But the set that contains nothing is the empty set. So there's only one of those. Now, the universe set, on the other hand, is the set that contains everything. So this is a little harder to describe, but it contains everything that we're talking about. So it depends on the context of the problem. And in fact, in some sense, the real numbers is kind of considered to be this universe set of all numbers. If you consider numbers that lie on the number line, for example, the real numbers is all of those numbers. It's a set of all those numbers. Okay, so that's a little harder to describe, unlike how we describe the empty set, but it's just a set that contains everything. So maybe I can write that. A set that contains everything. This kind of makes it look weird because it makes it look like everything is an element of this set, but I mean that everything is the set of all other elements. Anyways, natural numbers we saw is the set of 1, 2, 3, and so on. You can include 0 if you want, but if you do, I'll write a sub-0 there, a subscript of 0. Integers are the set of all of these natural numbers, negatives, and 0. So here 0 is included. We have negatives as well. So if I say integer, I mean positive or negative, whole number, and 0 as well. Rationals are a little harder to describe. These are the set of all fractions of integers. But the way you would write this is it would be the set of all a over b's such that a and b, a comma b, are elements of the set of integers, and, we use this and symbol, b is not equal to 0. You can also put a comma there maybe, but I like that and because we're using that kind of symbol we saw in the last video. Real numbers is a little harder to describe. This is basically the, I guess this is kind of one way to describe it maybe. The set of all x values such that either x is rational or x is not rational. Which sounds a little weird to me, because what it means to not be rational is just you're a real number that's not a rational number. So you can't write it as a set as a fraction of two integers. Like for example, pi is 3.14159 and so on. So we know the decimal expansion up to some point. But otherwise, if you stop, then you're approximating it as a rational number, basically. So it's kind of a weird thing, but as it turns out, there is no fraction, integer over integer, no rational number, such that pi is equal to. So this never happens, believe it or not. Now, it's not an obvious thing that pi is not rational. In fact, that's huge proof that's way beyond this class even. But there are proofs like that. Another example would be radical 2. Radical 2 is also not a rational number, but it is a real number. Why is it a real number? Because it can be approximated. In other words, it lives on the real number line. Specifically, it lives somewhere in between 1 and 2. Let's just say right here is radical 2. And pi is a little bit further than 3, right? So every number on the real number line, on a number line, is a real number, whether it's rational or not. Okay, power set of a set A is the set of all subsets of A. Now, subsets I haven't spoken of yet, but a subset is a set contained within the set. And in fact, here we have these two symbols here, subset and proper subset, which I'll discuss in a bit, of course. But I'm actually going to erase this below just to kind of describe an example using this subset symbol with the sets we've described above. For example, the natural numbers actually live inside of the integers. Why is that? Well, because the integers include the natural numbers. All the natural numbers live inside the integers. Even if you were to include 0, it's still a subset of this. Now, if it's a proper subset, that means equality is possible. Think of this like less than or equal to. It's kind of what this describes a little bit. And yeah, so this is not equal to, of course, or not the same set. It's possible that you could have two things that are the same set and you just don't know it, but you know one is definitely inside the other, but it's possible they're the same. I know it sounds weird. And a visualization of this is that a subset of a set is some kind of blob of elements that live inside of another blob of elements. So let's say this is a set A and this is a set B. If all the elements of B are also inside of the set of elements that are in the set A, then B is a subset of A. Okay, so that's explaining those two. But in fact, going even further, we can furthermore say if the denominator of rational numbers is 1, then you get A over 1, which is just A divided by 1 is A, so you get Z. So in fact, Z is a subset of Q, and we know Q is for sure a subset of R, because it's kind of in the definition, is that either it's in Q or it's not in Q. So everything in Q is automatically in R. So that's kind of a nice thing to see. We see this kind of chain of subsets of these number sets of numbers. Okay, intersections and unions. Intersection basically means taking kind of what two sets have in common, and union is taking a thing that is in either one of the sets or possibly in both. In fact, the visualization that comes to mind is what is known as a Venn diagram. So if you have two sets A and B, the intersection of these two sets is the set of all elements that is in A and also in B. Hence the and. Okay? So that's what intersection is. So this right here is A intersect B, the set of all elements that are both in A and also in B. Okay? Now that's for and. What about for or? Well, for or, it would be everything. So let me just kind of shade this all in blue. It's the set of all elements that are either in A or in B or possibly in both. So this right here, everything in blue, is the union of A and B. The set of all elements that are either in A or in B or in both. Okay. Cartesian product is a little different, but this is basically the set of all ordered pairs. The phrase Cartesian comes from Descartes, who was a logician from, I think, I don't actually know when he was from. Way long ago. I want to say 1600s. Probably could be 1500s. But in fact, that's where cardinality comes from too. They're all due to Descartes. He was in fact the kind of inventor of the Cartesian plane, which is the set of, well, you could think of it, the XY plane, basically. So the Cartesian product is basically, when it comes to real number line, is the XY plane. X-axis is the number line, and the Y-axis is another number line, and we're taking the cross product of those number lines. And what you end up getting is a set of all ordered pairs, all points, of two-dimensional numbers, basically. So if you were to consider A cross B, this is the set of all A comma B ordered pairs, such that A is in A and B is in B. So that's how you phrase that. Okay? Right. Set difference is a set without another set. So, like, for example, trying to think of, well, here's an okay example. The set of irrational numbers can be defined to be the set of real numbers without the rationals. So it's the set difference of the reals and the rationals, meaning everything that's in the reals that's not rational. So that's what set difference means. In fact, you can actually define the set difference using these symbols above. So I'll do that below. Maybe I'll actually do that in blue here below. In fact, let me erase this Venn diagram to show that. So let's say we want to take the set difference of A and B. That's everything that is in A that is not in B. So I want to say it is the set of things in A that are also not in B. So I want to say A and the complement of B. So I haven't described it yet, but it's here. Complement of A are things that are not in that set, but are in kind of the universal set. So going back to Venn diagrams, let's say we have this universal set U that contains everything, and we have these two sets that possibly intersect, A and B. Okay? So let's say A is here and B is here. Now, A without B is everything that is in A but is not in B. So A without B is just this, shading all of A except for this intersection part. So this is one way to describe it. And then notice, B complement is everything outside of B, but still within U, of course. So if I were to shade B complement, it'd be shading everything here, ignoring A. It'd be shading everything here that's not in the circle, everything outside of the circle of B. But now intersecting that with A is just shading that part of A only that doesn't include the B part. So, for example, again, irrationals are the set of all real numbers that are not rational. Okay, and complement of A, we kind of described that with the set difference, so that's kind of nice. Cardinality is a number of things in that set. So basically this is just number of elements. Which for a lot of these examples we have seen so far, these are infinite in cardinality. So there's infinitely many numbers in each of these sets, believe it or not. Sometimes you will have a set that has a finite amount of numbers. For example, you can have the set of all natural numbers such that x is less than 7. Now this is just equal to the set 1, 2, 3, 4, 5, 6, 7. And by counting, well, less than 7, not less than or equal to, so it doesn't include 7 itself. So by counting, you have 6 elements. So if we call this set S, then this implies that the cardinality of S is just the number 6. But again, for these ones, the cardinality is infinite, which is kind of strange because it seems like this is actually smaller than this set, which is smaller than this one, which is smaller than this one because of that containment we spoke about. But as it turns out, there are some infinities that are bigger than others, which is, again, a conversation that's a little deeper than where this course leads, but still something that you can think about. Okay, so now we're going to move on to the next idea. Right, so there actually is no next idea. We're just going to be taking a look at an example now. So this example will involve the sets A, B, and C, and we're asked to find these 4 things. So these operations of these sets. So we have this intersection, union, this set difference, and then this weird thing, which is a combination of those involving complement. Now, something I want to say maybe before we begin is that notice we can actually rewrite these using our notation of special sets. So for example, I can actually call this the intersection, I can call A, for example, the intersection of the natural numbers with the interval 1 to 5. There shouldn't be a ... there, I'm sorry. Yeah, my mistake, there's no ... it ends at 5. Yeah, sorry about that. So notice 1 through 5 is a set of all real numbers that are between 1 and 5, including 1 and including 5. So like pi, for example, is in here, 3.14159, and so on. But the intersection of that with the natural numbers is just the integers 1 through 5. And similarly, B is the intersection of the natural numbers with the closed interval 3 to 7. And then we can similarly say C is the natural numbers intersected with the interval 2 to 5. So I'm just bringing that up real quickly because that's something that's kind of interesting that comes to mind. I'm not going to be using this idea, but it's something you can kind of think about if you wanted to. And maybe see how you can use this information to find these. That's kind of an interesting idea, but I don't think it's really useful at all, actually. It's just a nicer way of writing it, possibly. Something nice to consider. Anyways, moving on to A. So A is asking us to find the intersection of A and B. And remember, intersection is the set of all elements that that are in A and also in B. So let's look at the intersection of A and B. So what is in A that is also in B? Is 1 in A? Yes. Is it also in B? No. So 1's not in that set. 2 is in A but not in B. 3 is in both. 4 is in both, and 5 is in both, and that's it. Okay, so I'll box this. What about the union of A and B? So these are things that are in A or in B, or in both. So for things in A, 1, 2, 3, 4, 5, and things that are in B, 3, 4, and 5 we've already included, and now we have 6 and 7. So this is the set of all things that are either in A or in B or possibly in both. So that's the union. Okay. A without B is a set of all things that are in A that are not in B. So that's actually looking at the intersection and then looking at things that are in A that are not in the intersection. So that's just 1 and 2. Notice that makes sense because this is the set of all things that are in A but not in B. Okay. Now this last one may take a little bit of thought, but we're taking the intersection of A with the complement of the union of B and C. So first let's investigate what this monstrosity is, and then we'll take the intersection of that with A. So maybe I'll write it out. A we know is the set of all integers from 1 through 5. And now let's look at this. So what is the complement of B union C? So B union C, now we have this at C, the set of all things that are in C and also or in B. But notice C and B both contain 3 and 5, but B does not contain 2 that C does. So let me just say B union C is equal to 2, 3, 5, or 2, 3, 4, 5 because B includes 4, 6, and 7. There we go. So notice this is a set of all elements that are in B or C or in both. Okay. Okay, now what's interesting here is that if we're taking the complement of this, we're looking at things that are not in this. So if we want to take a look at the complement of this, then this is the set of all elements that are not these. Now again, speaking of universe sets, kind of what we saw on the last screen a little bit, we spoke of universe sets. Universe sets are important here because if you're not in this, then what are you in, right? So elements that are not in this set are other things you can possibly think of, but the weird thing for me is that there is, I guess you can say 1 isn't in this, and then what else? Maybe 8, 9, 10, and so on. But that's assuming that our universe set contains integers. It can be everything else. So this is a little weird for me to kind of describe, but I will say that of all the numbers we've seen here, so let me just kind of assume, which is not a really good thing to do in this case, assume that our universe set U is the set of all numbers from 1 to 7, which I think is an okay assumption here because these are the only integers that we're kind of considering. So with that being said, this would be the single element 1. 1 is the only thing that is not in the union of B and C. And that matters because when you take the intersection of A with that single element, the only thing they have in common is 1. So this is just a single element 1. If they had nothing in common, then this would be the empty set. Okay? And by the way, 2 things that have an intersection of the empty set are known as mutually exclusive. So they share nothing in common. In fact, the Venn diagram would look like this, which is kind of funny to look at. Right? They don't intersect at all. Their intersection is empty, in other words. But in this case, the intersection is not empty. And even if our universe wasn't 1 through 7, if it was beyond this, in fact, if it was every number, for example, the set of all things that are not in this, but also in A, still must be 1, no matter what your universe set is, but that just made our conversation a little easier, I think. Okay, so believe it or not, that actually concludes all I want to say as far as sets are concerned, and I thank you all for watching, and I'll see you in the next video.